Right now, as you read these words, 100 trillion neutrinos are passing through your body. Every second,
The
100
convergence is
trillion.
imminent. This
They
artifact
come
will
from the
unlock its
sun
secrets.
8 minutes
Observe the
old in
reaction.
light. They come
Incredible
from the
power.
Big Bang itself,
Initiating surface
13.8 billion
transformation.
years in the making.
Observe the
They come
convergence.
from
Perfect.
supernovae that
Parameters are
exploded when
stabilizing.
Earth was still molten rock, their light only now reaching the edge of our cosmic neighborhood. You don't feel them. They pass through flesh and bone like ghosts, through walls, interacting with nothing, touching nothing, caring for nothing. But they're there. They've always been there. And now, after a century of patient observation, after decades of mathematical reasoning, after generations of scientists building telescopes and satellites and underground detectors, you know they're there. That knowing changes everything. Because if invisible particles can stream through you every moment of your life undetected until someone thought to look, what else is happening that you can't see? What else is real but hidden? What truths are passing through your awareness right now, waiting for the right question, the right instrument, the right moment of clarity? The answer, it turns out, is almost everything. The universe you think you know, the one with galaxies and stars and planets, the one that began with a Big Bang 13.8 billion years ago, the one that stretches 93 billion light years from edge to edge, that universe is not wrong. The observations are real, the measurements are accurate, the math checks out, but it's incomplete, profoundly, staggeringly incomplete, like looking through a keyhole and thinking you've seen the whole house. Like standing in fog that limits your vision to 3 meters in every direction and assuming that's all the ocean there is. Like being born in a small room and never knowing that beyond the walls lies not just another room, but an infinite mansion with infinite rooms, some identical to yours, some utterly alien, all existing simultaneously in a structure so vast that the word vast loses meaning. This is the story of how we discovered the keyhole, how we measured the fog, how we found the door in the wall and glimpsed what lies beyond. Not through speculation or philosophy or wishful thinking, but through patient observation, rigorous mathematics, and the kind of intellectual honesty that admits ignorance while pursuing truth anyway. It's the story of Edwin Hubble peering through a telescope, night after night, recording galaxies that shouldn't be moving. Of George Gamow, scribbling equations that predicted an echo from creation itself. Of Arno Penzias and Robert Wilson, scraping pigeon droppings off an antenna, trying to eliminate noise that turned out to be the most important signal in the history of cosmology. It's the story of Alan Guth lying awake at 3 in the morning, unable to sleep, because a single thought kept circulating through his mind like a prayer. What if space itself grew? Of André Linde spending 30 years refining a theory most thought was crazy patient, as stone waiting for technology to catch up to mathematics. Of Saul Perlmutter coordinating teams across continents to photograph distant dying stars, only to discover that the universe itself was dying differently than anyone expected. These are not stories of genius striking like lightning. They're stories of patience rewarded, of decades spent asking the same question from different angles, of being wrong, adjusting, being wrong again, adjusting again until slowly, so slowly that individual lifetimes barely register progress, the shape of truth emerges from fog. And the shape that emerged, the observable universe, everything humans have ever seen, measured, cataloged, understood, is not the universe. It's a bubble, a tiny transparent sphere floating in something incomprehensibly larger. And that larger thing, it might contain other bubbles, infinite other bubbles. Each one a complete universe unto itself with its own galaxies, its own stars, its own laws of physics. You might be living inside one thought in the mind of something so vast that the word Gondiad is too small to contain it. Or you might be living inside a simulation run on computational substrate that exists in dimensions you can't perceive. Or you might be living on a two-dimensional holographic boundary, and the three-dimensional space you move through is a projection, like a movie on a screen, real but not fundamental. Or all three might be true simultaneously, different ways of describing the same underlying reality, like blind men touching different parts of an elephant, and each reporting what they find. The mathematics suggests this. The observations hint at it. The greatest minds of the last century have converged on it from different directions, using different tools, arriving at the same unsettling conclusion. You are inside something much bigger than you can see. And here's the strange part, the part that makes this more than abstract philosophy. You can prove it. Not with speculation, not with faith, with numbers, with measurements, with the same kind of rigorous observation that proved Earth orbits the sun, that germs cause disease, that atoms exist even though you can't see them. The proof requires patience. It requires following a chain of reasoning that took a century to forge link by link, observation by observation. It requires accepting that reality is stranger than common sense suggests, while simultaneously demanding that every strange claim be backed by evidence. But if you have that patience, if you're willing to follow the path from familiar ground to alien territory, step by careful step, then by the end of this journey, you'll understand something profound. The horizon you can see is not the edge of what exists, it's the edge of what you can observe. And beyond that edge lies not darkness, not nothing but more. Possibly infinite more. Possibly more than infinity, if such a thing makes sense. And the most beautiful part, the part that makes all of this more than just cosmic accounting. You're not separate from it. You're not a passive observer watching the universe from outside. You're made of atoms forged in the cores of dying stars. Your arrangement of matter complex enough to contemplate its own existence. You're the universe experiencing itself locally, temporarily, magnificently. Carl Sagan said it poetically, we are a way for the cosmos to know itself. But after understanding inflation, holography, quantum observation, eternal bubbles, and the participatory nature of reality, you'll see that's not poetry, it's physics. Let's begin. On a clear night in 1923, Edwin Hubble sat alone in the dome of the Mount Wilson Observatory, 100 feet above Pasadena, California. The telescope beside him, the Hooker telescope, 100 inches of carefully ground glass and steel, pointed toward a faint smudge of light in the constellation Andromeda. Most astronomers thought that smudge was a nebula, a cloud of gas inside the Milky Way rotating slowly, perhaps birthing stars. But Hubble had noticed something strange in photographic plates exposed over many nights. Individual stars within the nebula that brightened and dimmed with regular periods. Variable stars. Cepheid variables, to be precise, stars whose brightness oscillates based on their intrinsic luminosity. And if you know a star's intrinsic brightness and you measure how bright it appears, you can calculate how far away it is. Like knowing the wattage of a light bulb and using how dim it looks to determine distance. Hubble did the math. The numbers didn't make sense. The Andromeda Nebula wasn't a nebula at all. It was too far away, almost 1,000,000 light-years distant, far beyond the known boundaries of the Milky Way. It was another galaxy, an island universe. And if one existed, how many more might there be? The universe had just gotten bigger, much bigger. But Hubble wasn't finished. Over the next 6 years, he photographed dozens of galaxies, measuring their distances and their light. And he noticed something else, something that would change everything. The light from distant galaxies was shifted toward the red end of the spectrum. Redshift. Like the Doppler effect that makes an ambulance siren drop in pitch as it speeds away, light from these galaxies was stretched wavelengths, elongated energy, reduced. They were moving away. All of them. The farther the galaxy, the faster it receded. In 1929, Hubble published his findings. The universe was not static. It was expanding. Space itself was growing, carrying galaxies along like raisins in rising bread dough. If you were in your 20s in 1929, perhaps just starting a career, maybe newly married, you lived through the year the universe changed. The cosmos you'd learned about in school, eternal and unchanging, suddenly had motion. History. A direction. That single paper transformed everything humanity thought about existence. If space was expanding now, you could run the movie backward. Shrink space. Bring galaxies closer together. Keep shrinking. Eventually, everything would converge at a single point. A moment of origin, a beginning, the Big Bang. The name came later, coined by Fred Hoyle in a radio broadcast meant as mockery. Hoyle didn't believe in a cosmic beginning. But the evidence kept mounting, and one piece of evidence, predicted by theory but unobserved for decades, would seal the case. George Gamow was not like other physicists. Russian-born, exuberant, prone to thought experiments involving vodka and cosmological constants, he approached problems with playful seriousness. In 1948, working with Ralph Alpher and Robert Herman, he asked a simple question. If the universe began in a hot, dense state and has been expanding ever since, what happened to all that heat? The early universe would have been unimaginably hot, too hot for atoms. Matter existed as plasma electrons and nuclei flying free, scattering photons in every direction. Like fog so thick that light can't travel more than a few centimeters before hitting something. But as the universe expanded, it cooled. At about 380,000 years after the Big Bang, temperature dropped enough for electrons to bond with nuclei. Atoms formed. The fog cleared. Photons could suddenly travel freely through space. And those photons are still traveling. Stretched by cosmic expansion, redshifted from visible light to microwaves, but still there. Everywhere. filling all of space like thermal radiation from a cooling oven. Gamow predicted this cosmic microwave background would have a temperature around 5 Kelvin, a faint glow, the afterglow of creation itself. For 16 years, no one looked for it. It seemed too difficult to detect, too speculative to waste resources on. The prediction set in journals acknowledged but not pursued. Until 1964. Arno Penzias and Robert Wilson were not cosmologists. They were engineers at Bell Labs in New Jersey working on satellite communications. They'd built a large horn antenna designed to detect faint radio signals bouncing off weather balloons. But the antenna had a problem: noise. No matter what frequency they tuned to, no matter which direction they pointed, the antenna there was always background static, a persistent hiss. Annoying, unexplained. They checked everything. Calibrated instruments, shielded electronics, eliminated Earth-based radio interference. The noise remained. Then they noticed something else. Pigeons had been nesting inside the antenna. The antenna was, as Penzias would later describe with characteristic understatement, covered with a white dielectric material. Pigeon droppings, hardened layers of them. They cleaned the antenna, scrubbed it, removed every trace of organic contamination, pointed it at empty sky. The noise persisted. Same intensity, same frequency, same everywhere they looked. Finally, after exhausting every earthly explanation, they called physicists at nearby Princeton. Robert Dickey's team had been preparing to search for Gamow's predicted microwave background. When Dickey heard about the noise, he understood immediately. "We've been scooped," he told his team. "The noise wasn't noise, it was signal, the echo of the Big Bang. Cosmic microwave background radiation, exactly as Gamow predicted, with a temperature of 2.7 Kelvin. Penzias and Wilson had accidentally discovered the most important piece of evidence for the Big Bang theory. They would win the Nobel Prize in 1978. If you were alive in 1965, if you remember that year, the music, the news, the feeling of the times, then you lived through one of the greatest scientific discoveries in history. The year we found creation's echo. The year the universe got older overnight from perhaps 2 billion years to somewhere between 10 and 20 billion. Everything cosmology textbooks said became obsolete in a single announcement. But here's where the story gets strange. When you measure the cosmic microwave background carefully, and over the next 5 decades, satellites like COBE WMAP and Planck would measure it with extraordinary precision, you discover something odd. The photons making up the cosmic microwave background left their source 380,000 years after the Big Bang. They've been traveling ever since. If the universe is 13.8 billion years old, those photons have been traveling for 13.8 billion years, minus 380,000 years. Close enough to 13.8 billion years. A photon traveling for 13.8 billion years should cover a distance of 13.8 billion light years. But it doesn't. The source of those photons, the plasma surface from which they were emitted, is now 46 billion light years away. How did something travel 46 billion light years in 13.8 billion years? Did photons move faster than light? No. The speed of light is constant. Did time work differently back then? No, more space expanded. While the photons were traveling, space itself stretched, like ants crawling across a balloon's surface while someone inflates it. The ants move at constant speed, but the surface beneath them grows. By the time they reach their destination, the distance they've crossed is larger than the distance they traveled. Photons that left 13.8 billion years ago have crossed space that's now 46 billion light years wide. This creates the observable universe, a sphere centered on Earth, not because Earth is special, but because every observer sees their own sphere with a radius of 46 billion light years. Diameter 93 billion light years. That's everything humanity can see. Every galaxy cataloged, every star counted, every planet imagined, all contained within a sphere 93 billion light years across. But here's the question that haunted cosmologists for decades, the question that drives this entire story. Does the universe stop there? Is the cosmic horizon the sphere beyond which light hasn't had time to reach us, the edge of existence? Or is it just the edge of what we can observe? If you draw a circle around yourself with a radius equal to how far light can travel in your lifetime, does the world end at that circle, or does it continue beyond? Unseen but real, common sense says the universe continues. Space doesn't care about our observational limits. If physics works here, it probably works there too. But for decades, this was assumption. Reasonable assumption, but still assumption. No way to test it. No evidence beyond logic. Until one sleepless night in 1979, when a 32-year-old physicist named Alan Guth had an idea that changed everything. Alan Guth couldn't sleep. It was 3 in the morning, December 10th, 1979. He sat at his desk in his apartment near Stanford, staring at equations scrawled across notebook pages. For weeks, he'd been thinking about a problem in cosmology that most physicists considered minor, a technical issue, the kind of thing you work on if you can't get a position studying more interesting phenomena. The problem was called the flatness problem. When you measure the geometry of space, whether it curves back on itself like a sphere curves away, like a saddle, or extends flat like an infinite sheet, you expect to find some curvature. The universe has mass. Mass curves space. Einstein's general relativity says so. Space should be curved. But measurements kept showing flatness. Not approximate flatness. Precise flatness. The universe's geometry was flat to within measurement error, which by the 1970s was becoming impressively small. This was strange, because in the early universe, even tiny deviations from flatness would have been amplified over time. If the universe started even slightly curved, it should be extremely curved now. Either collapsed back on itself into a big crunch, or expanded so fast that matter never clumped into galaxies. The fact that we exist in a universe with galaxies and stars means the early universe was flat to absurd precision. 1 part in 10 to the 60th power, like balancing a coin on its edge, not just once, but a trillion times in a row, and having it stay balanced every time. Either the universe won at an impossible cosmic lottery, or something made it flat. Guth thought he knew what. What if in the first fraction of a second after the Big Bang, space didn't just expand, it inflated exponentially, faster than light. Not objects moving through space, but space itself doubling in size every tiny instant. Like taking a wrinkled balloon and inflating it to the size of Earth. The wrinkles don't disappear, but they get stretched, so smooth you can't detect them anymore. If space inflated by a factor of at least 10 to the 26th power, a trillion times in a fraction of a second, any initial curvature would be flattened. The universe would look geometrically flat, not because it started that way, but because inflation stretched it flat. Guth scribbled faster. The math worked. Inflation explained flatness. It also explained another puzzle: why the cosmic microwave background looks the same in every direction, even though regions separated by billions of light years should never have been in contact, never had time to equilibrate to the same temperature. If inflation happened, those regions were in contact. For inflation, they were close together. Inflation pushed them apart so fast that light hasn't had time to travel between them since. They look disconnected now, but they weren't always. In his notebook, Guth wrote a single sentence and drew a box around it. Spectacular realization. The next morning, he began working out details. Within months, he'd published the theory. Within years, other physicists had refined it, fixed problems, developed variants. By the 1990s, inflation had become the leading explanation for cosmic structure. And it had one consequence nobody expected. If inflation could start, it might not stop everywhere at once. André Linde was sitting in his Moscow apartment when he saw the flaw in Guth's original inflation theory. It was elegant. It solved problems. But it had an issue with how inflation ended. Guth's version required a carefully tuned process to transition from inflation to normal expansion. Too carefully tuned. Like trying to stop a runaway train by hitting the brakes at exactly the right millisecond. Possible in theory. Unlikely in practice. Linde realized you didn't need such precision if you changed the mechanism slightly. Instead of inflation being driven by a field stuck in a high-energy state that suddenly dropped, if the field varied randomly across space, in some regions the field's value would be high, driving continued inflation. In other regions, it would drop below a threshold, ending inflation and beginning normal expansion. As high field regions continued inflating, they'd grow exponentially. Low field regions would stop growing so fast. But here's the key: high field regions inflate faster than low field bubbles can form within them. Imagine water boiling. Bubbles form constantly. But if water volume doubled every second, bubbles would appear continuously yet never merge, always separated by exponentially growing water. Each bubble is a universe. Not a universe in some metaphorical sense. A universe. With its own expansion rate, its own galaxies, its own stars. Our observable universe, the 93 billion light-year sphere we can see, is inside one bubble. Outside our bubble space is still inflating exponentially. And in that inflating space, new bubbles form, constantly, eternally. This is eternal inflation. Linde proposed it in 1983. Most physicists thought it was wild speculation. Interesting mathematics, but untestable. How could you ever prove the existence of other bubble universes if they're beyond our cosmic horizon? Lindy didn't mind skepticism. He'd learned patience growing up in Soviet Russia where speaking too freely could end careers. He spent 30 years refining the mathematics, exploring implications, waiting for observations to catch up. And in 2010, they did. Stephen Feeney was a PhD student at University College London when he decided to search for bubble collisions. The idea was simple. If eternal inflation is correct, our bubble universe should have nucleated from inflating space billions of years ago. Other bubbles nucleated around the same time. If two bubbles happen to nucleate close together, they might collide before expansion pushed them apart. A collision between bubble universes would be violent. Different vacuum states meeting at light speed, the boundary would release enormous energy. And that energy would leave an imprint on the cosmic microwave background, a circular pattern, like ripples on a pond's surface. Feeney wrote algorithms to search Planck's satellite data for such patterns. The satellite had mapped the cosmic microwave background with unprecedented precision, measuring temperature variations to millionths of a degree. Most patterns in the data are random fluctuations. Quantum noise from the early universe stretched to cosmic scales by inflation. You expect to see temperature variations everywhere, but they should be statistically uniform. No preferred direction, no geometric structure. Feeney searched for exceptions, circular patterns, concentric temperature rings, and features too organized to be random. He found four circular patterns, each billions of light years across with temperature variations that match theoretical predictions for bubble collisions almost exactly. The scientific community reacted with cautious interest in healthy skepticism. Other teams analyzed the same data. Some found additional patterns. Others argued the patterns were statistical flukes, random noise that happened to look organized. As of 2026, the evidence remains suggestive but not conclusive. The patterns are there, the question is what they mean. But here's what even the skeptics agree on. If eternal inflation is correct, collision patterns should exist. Finding candidates in the data is not surprising. The debate is over confidence levels and statistical significance. And that debate, that careful weighing of evidence, that patient accumulation of observations over decades, that's how science works. Not through sudden revelation, through gradual refinement, through arguments in journals and conferences, through better instruments collecting better data that slowly, incrementally resolves uncertainty. Which brings us to the most unsettling implication of eternal inflation. If it's correct, our observable universe is not just one bubble among many. It's one bubble among infinite bubbles. Eternal inflation doesn't produce a handful of universes. It produces an infinite multiverse, constantly generating new bubbles forever. No beginning in time, the inflating space has always existed. No end in time, it will always exist, and every bubble that forms settles into a vacuum state. A configuration of fields and forces and particles that determines how physics works inside that bubble. String theory suggests there are approximately 10 to the 500th power possible vacuum states. Each one corresponds to a different set of physical constants, different strengths of gravity, different masses for electrons, different cosmological constants. Most vacuum states don't allow atoms to form, or if atoms form, they're unstable. Or if they're stable, gravity is too strong and everything collapses into black holes immediately, or too weak and matter never clumps into stars. Only a tiny fraction of possible vacuum states permit the kind of stable, long-lived structures necessary for complexity, for chemistry, for life, for consciousness. And we find ourselves in one of those rare bubbles, not because we're special, but because consciousness can only arise in bubbles where the physics permits consciousness. It's called the anthropic principle, not a fundamental law, but a selection effect, like asking why fish always find themselves in water, not because water is the only environment, but because fish die everywhere else. If eternal inflation and the string landscape are both correct, then somewhere in the infinite multiverse, every possible set of physical constants is realized. Every stable configuration exists. There are bubbles where electrons are 10 times heavier and chemistry works completely differently. There are bubbles where the cosmological constant is larger and galaxies never form. There are bubbles where fundamental forces have different strengths and atoms are shaped differently. And scattered among those sterile universes are bubbles like ours, rare, precious, capable of supporting the kind of complexity that leads to stars, planets, and eventually minds capable of asking, what else is out there? You're in one of those bubbles, not by design, by chance, by the brute force of infinity, ensuring that every possibility given enough trials is realized. This is the picture of reality that emerged from inflation theory over 40 years of refinement. But it raises an immediate question. If our observable universe is just a small region inside one bubble, and bubbles are separated by exponentially expanding space, and different bubbles have different physics, then how can we possibly test this? How do you confirm the existence of something you can never observe? The answer comes from a completely different direction, from studies of black holes, from quantum mechanics, from a principle so strange that when it was first proposed, most physicists rejected it as absurd. The holographic principle. Juan Maldacena was 29 years old when he proved that a five-dimensional universe with negative curvature is mathematically equivalent to a four-dimensional quantum field theory on its boundary. That sentence requires unpacking. Start with something simple. A can of soup. The can has three-dimensional space inside. The can's surface, the metal boundary, is two-dimensional, a curved sheet wrapping around the volume. Common sense says the volume contains more information than the surface. More space means more possible arrangements of atoms, more entropy, more ways things can be configured. But in 1997, Maldacena proved this intuition wrong, at least for certain carefully constructed spacetimes. He studied anti-de Sitter space, a universe with negative curvature that curves away from itself like a saddle. 5 dimensions. Exotic. Nothing like our universe. And he proved mathematically that everything happening in that 5-dimensional volume could be completely described by physics on the 4-dimensional boundary. Not approximately described, not summarized, completely encoded. Every particle trajectory, every field fluctuation, every interaction, everything in the 5-dimensional interior has a corresponding representation on the 4-dimensional surface. The 3-dimensional reality is a hologram projected from 2-dimensional information. This is the ADS/CFT correspondence. Anti-de Sitter space corresponds to conformal field theory. Maldacena published it in 1997. Within a year, it became the most cited paper in theoretical physics. Consider what this means. You think you live in 3-dimensional space. You move forward, backward, left, right, up, down. 3 independent directions, volume, depth. But Maldacena's proof suggests that 3-dimensional experience might emerge from 2-dimensional information. Like a hologram on your credit card, the card's surface is flat, 2-dimensional. But when light hits it correctly, a 3-dimensional image appears, depth emerging from flatness. What you perceive as volume might be projection, computation, information processing on a distant 2-dimensional screen, creating the illusion of depth. The idea didn't originate with Maldacena. It came from studying black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something strange about black hole thermodynamics. A black hole has entropy, a measure of disorder of hidden information. For normal matter, entropy scales with volume. Double the volume, double the entropy. More space means more possible arrangements. But for black holes, entropy is proportional to surface area, specifically the area of the event horizon, the boundary beyond which nothing escapes. A black hole's information content is determined by its 2-dimensional surface, not its 3-dimensional volume. This was bizarre. It violated everything thermodynamics said about how information scales. Gerard de Hooft and Leonard Susskind took this observation further in the 1990s. They proposed the holographic principle. The maximum amount of information in any region of space is determined by the area of the boundary, not the volume inside. This suggests something profound. 3-dimensional space might not be fundamental. It might emerge from information encoded on 2-dimensional boundaries like holograms emerge from interference patterns on flat surfaces. Apply this to the observable universe. The cosmic horizon, the sphere 46 billion light-years in radius beyond which we can't see, because light hasn't had time to reach us, might not just be an observational limit. It might be an information boundary. All the information about everything inside the observable universe, every galaxy, star, planet, atom thought you've ever had, might be encoded on that distant 2-dimensional surface. And the 3-dimensional space you experience, a holographic projection from boundary data. You think you're moving through 3-dimensional space, but fundamentally you might be patterns of information on a 2-dimensional surface experiencing the illusion of depth. This sounds like mysticism, but it's mathematics, rigorous, testable mathematics. Maldacena's proof works for anti-de Sitter space. The question is whether it generalizes to our universe. Our universe isn't anti-de Sitter. It has positive cosmological constant dark energy and different curvature properties. Extending a DS/CFT to de Sitter space, which better describes our cosmos, remains an open problem. But the principle is clear, and it connects directly to eternal inflation. If the observable universe is a bubble in eternally inflating space, and if the holographic principle applies, then the boundary of our bubble isn't just where inflation ended and normal expansion began. It's where information is encoded. Everything you see, every observation you make, every measurement you take, all of it might be reading information off a distant two-dimensional screen. The cosmic horizon, the holographic boundary, and beyond that boundary, not more three-dimensional space filled with galaxies and stars. Something else, something undefined, possibly the inflating space between bubbles not yet crystallized into specific reality, possibly quantum foam, all possible states superimposed until observation collapses them into definiteness. Which brings us to the strangest part of this story, the part where observation itself becomes fundamental. In 1927, Niels Bohr stood before a room of physicists in Copenhagen and made a claim so bizarre that Einstein spent the rest of his life arguing against it. Bohr claimed that quantum systems don't have definite properties until measured. An electron doesn't have a position or a momentum until you check. For a measurement, it exists in a superposition, all possible positions, simultaneously all possible momentums at once. Only when observed does the superposition collapse into a single definite state. This wasn't philosophy, it was mathematics. The equations of quantum mechanics demanded it, and experiments confirmed it. The double-slit experiment remains the clearest demonstration. Fire electrons one at a time through two slits. Don't measure which slit they pass through. They create an interference pattern on the detector screen, alternating bands of hits and misses exactly like waves interfering with themselves. Each electron passes through both slits simultaneously, but place a detector at the slits to check which one the electron uses. The interference pattern vanishes. You get two bands corresponding to electrons going through one slit or the other. The act of measurement changes the outcome. Not because the measurement device physically disturbs the electron, though that happens too, but because measurement forces reality to choose, to collapse from superposition into definiteness. Before measurement, electron in both slits following all paths interfering with itself. After measurement, electron in one slit following one path behaving like a particle. Einstein hated this. He famously wrote to Max Born, "God does not play dice with the universe," by which he meant reality must be definite whether we measure it or not. Our measurements reveal pre-existing facts. They don't create facts. Bohr disagreed, and decades of experiments have sided with Bohr. But here's where it connects to cosmology. If quantum systems exist in superposition until observed, and if the early universe was governed entirely by quantum mechanics, as it must have been when everything was smaller than atomic scales then, what was the state of the universe before observers existed? Was the entire cosmos in superposition, all possible configurations overlapping? Did the Big Bang produce a wave function describing every possible history simultaneously? And only when conscious observers evolved did reality collapse into the specific history we experience. John Wheeler, one of the great physicists of the 20th century, took this seriously. He proposed the participatory universe, the idea that observation isn't passive reception of pre-existing facts, but active participation in creating reality. He illustrated it with a thought experiment. Imagine light from a distant quasar passing a massive galaxy. Gravity bends light. The quasar's photon can travel around either side of the galaxy. Two paths, billions of light years long. The photon started its journey billions of years ago, long before Earth existed. Now place a detector on Earth. You can configure it two ways. Either measure which path the photon took, left or right around the galaxy, or don't measure path. Instead, measure whether the photon shows interference as if it took both paths. Wheeler's delayed choice: you decide how to measure after the photon is already en route, after it's already passed the galaxy. Your choice now affects which path it took billions of years ago. The photon doesn't take a definite path until you measure it. Even if the measurement happens billions of years after the photon passed the choice point, measurement doesn't just affect the present. It reaches backward, forcing the past itself into definiteness. This has been tested. Delayed choice experiments confirm Wheeler's prediction. The universe waits for observation before committing to history. Now apply this to the cosmic horizon. Everything beyond the cosmic horizon is unobservable, not because it's too far away in some abstract sense, but because light from those regions hasn't reached us. We have not and cannot observe what's there. If quantum mechanics applies, and it does especially in the early universe when everything was quantum scale, then regions beyond the horizon might not be in definite states. Not, we don't know what's there, but there is no definite what is there until observation occurs. The observable universe isn't just the region we can see. It might be the only region that exists in definite form. Beyond the horizon, quantum superposition, all possible configurations overlaid, undefined. And as expansion continues, more regions cross into the observable universe. Light from previously unreachable areas finally reaches us. We observe them for the first time. And in that moment, the moment of observation, those regions collapse from superposition into definiteness. We're not discovering pre-existing universe. We're participating in its definition. This is where holography, eternal inflation, and quantum observation converge. The cosmic horizon is an information boundary. The holographic principle says volume information is encoded on boundaries. Quantum mechanics says unobserved systems exist in superposition. Eternal inflation says space beyond our bubble is still inflating, possibly in undefined state. Put it together. Our observable universe is a bubble where reality has crystallized into definiteness through the act of observation. The boundary, the cosmic horizon, encodes all information about interior states. Beyond the boundary, inflating space in quantum superposition, undefined, waiting for observation to collapse possibilities into actualities. You are not inside a universe. You are inside a region of defined reality carved out of infinite undefined possibility by the act of consciousness observing. And that act, observation, measurement, consciousness, is not peripheral to physics. It's central. It's the mechanism by which possibility becomes actuality, by which the universe transitions from all states at once to this specific state now. You're not watching reality, you're creating it, locally, temporarily. But really, this is not mysticism. This is quantum mechanics applied to cosmology. This is the mathematics that emerges when you take seriously both the holographic principle and the measurement problem. And it leads to one final vertiginous possibility. In 2003, a philosopher named Nick Bostrom published a paper that went viral among physicists, computer scientists, and late-night dorm room debaters. He presented a simple logical argument. 3 possibilities, at least one of which must be true. First possibility. Nearly all civilizations at humanity's current level of development go extinct before achieving the computational power to run high-fidelity ancestor simulations. Detailed simulations of conscious beings living in realistic universes. Second possibility. Advanced civilizations capable of running such simulations choose not to, perhaps for ethical reasons, perhaps because they find it boring. Third possibility. We are almost certainly living in a simulation. The logic is straightforward. If civilizations survive long enough to develop simulation technology, and if they have any interest in running simulations, they'll run many, thousands, millions. The computational resources available to an advanced civilization are vast. Running detailed simulations of conscious beings would be trivial for technology only a few centuries ahead of ours. If many simulations run, the number of simulated consciousnesses will vastly outnumber biological ones, by factors of millions or billions or more, which means any given conscious entity, like you, is statistically more likely to be simulated than original. Like a lottery in reverse. Most tickets win. This sounds like science fiction. But when physicists started examining this argument seriously, they looked for evidence. Signs that our universe might be computational. They found several suggestive features. First, fundamental limits to measurement precision. Quantum mechanics imposes hard limits. You cannot measure position and momentum simultaneously with arbitrary precision. The Heisenberg uncertainty principle prevents it, not because instruments are imperfect, but because reality itself is fuzzy at small scales. Similarly, space-time itself has minimum scales. The Planck length 10 to the minus 35th power meters represents the smallest meaningful distance. Below that, quantum fluctuations make the concept of distance break down. The Planck time 10 to the minus 43rd power seconds is the smallest meaningful time interval. These look like pixelation, like a minimum resolution, like the universe renders reality at specific scales and no finer exactly as a simulation would to conserve computational resources. Second, observer-dependent rendering. Quantum superposition until measurement. This is precisely how an optimized simulation would work. Don't compute what's not observed. Keep unobserved regions in compressed state superposition and only calculate definite values when observation demands it. Video games do this. They don't render the entire game world constantly. They render what the player sees. Everything else exists in low-resolution, placeholder state until needed. The universe does the same. Quantum systems remain in superposition, a computationally efficient state representing all possibilities simultaneously until observation requires computing a specific outcome. Third, mathematical structure. Physical laws can be written as equations, relatively simple equations considering the complexity they generate. Einstein's field equations fit on a t-shirt. The Schrödinger equation is one line. Maxwell's equations for electromagnetism, 4 equations total. From these simple rules emerges all the complexity of chemistry, biology, weather, galaxies, consciousness, enormous diversity from compact foundations. This resembles code, elegant algorithms that generate complexity through iteration. Conway's game of life creates intricate patterns from 4 simple rules. Cellular automata produce endless variety from minimal programming. If the universe is a simulation, its laws would be algorithms, and algorithms are mathematics executed. Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematics describe physical reality so perfectly? If reality is computation, mathematics isn't mysteriously effective. It's the language of computation. The universe isn't described by math. It is math being executed. Max Tegmark takes this to its logical conclusion. He argues the universe doesn't just follow mathematical laws. The universe is a mathematical structure. Physical reality is mathematics. What we call matter and energy and space-time are all just mathematical objects, solutions to equations existing in some Platonic realm of pure mathematics. And if all mathematical structures exist, then every possible universe exists. Every consistent set of equations defines a universe. Somewhere in the space of all possible mathematics, every configuration is realized. This is Tegmark's level 4 multiverse, beyond level 1 regions outside our horizon. Beyond level 2, other bubbles from eternal inflation. Beyond level 3, parallel branches from quantum measurement. Level 4 proposes that every possible mathematical structure exists as a universe. We're in one such structure, one set of equations, one configuration of mathematical rules, but infinite others exist. Universes with different dimensionality, different symmetries, different fundamental constants, different mathematics entirely. And here's where it loops back to simulation. If the universe is mathematics, and if mathematics can be computed, then advanced civilizations could simulate universes by computing mathematical structures. They don't need to build physical universes. They run the equations. The simulation is the universe. And if they run the equations on computational substrate, whatever serves as their computers, then the simulated universe exists on that substrate. The substrate is in some base reality with its own physics. And the simulation runs within it, following different physics, different rules, experiencing different time. From inside the simulation, you can't detect the substrate directly. You experience the simulated physics. You measure the simulated constants. You observe the simulated spacetime. But certain features might hint at the computational nature. The holographic principle, for instance. If reality is fundamentally two-dimensional information projected into three-dimensional experience, that's exactly what you'd expect from efficient computation. Store data on two-dimensional arrays. Compute three-dimensional space from that data. Minimize redundancy, or quantum mechanics. Superposition is computationally efficient. You don't calculate every particle's exact state every instant. You calculate probability distributions. Only when measurement occurs do you compute specific values. This conserves resources dramatically. Or the cosmic horizon, the boundary beyond which you cannot observe. From a computational perspective, that's the edge of what needs to be rendered. Beyond the horizon, the simulation can use placeholder values, low-resolution approximations, or simply not compute at all. No observer can check. Different bubble universes in eternal inflation. Different simulation instances, running different parameter sets, all executing on the same substrate in base reality. The string landscape of vacuum states. Different initial conditions for different simulations, each one a different experiment in physics. It all fits, disturbingly well. But here's the question that keeps philosophers awake. If we're in a simulation, what about the base reality running the simulation? Is base reality also a simulation? And if so, what runs that simulations all the way down? Or is there an ultimate base reality, the foundation layer, the original universe, where the first civilization arose and built the first simulation? And if there is such a base reality, how do we know we're not it? Maybe we're not in a simulation. Maybe we're the original, the base layer, the foundation on which future civilizations will build simulations of their own. Or maybe the distinction doesn't matter. If a simulation is perfect, if it follows consistent rules, if consciousness within it is genuine, if subjective experience is real, then simulated versus real becomes meaningless. Pain is pain, love is love, discovery is discovery. The substrate on which consciousness runs biological neurons, silicon chips, quantum fields, or something unimaginable in base reality, doesn't change the reality of experience. If you're conscious, you're conscious. Implementation details don't diminish that. And there's something profound here, something that ties together everything we've discussed. If the universe is computation, and if consciousness is information, processing, reaching self-awareness, and if reality emerges from holographic boundaries, encoding information, and if observation participates in collapsing quantum superpositions, then consciousness isn't peripheral to physics. It's central. It's how information processes itself, how the universe computes, how possibility becomes actuality, how undefined quantum foam crystallizes into definite classical reality. You are not separate from the universe. You are the universe's way of experiencing itself, of observing itself, of computing itself into definiteness. Carl Sagan said we are a way for the cosmos to know itself. Now you know why that's not poetry. It's physics. The year was 1980 and cosmology had a flatness problem. Not a problem anyone outside physics departments cared about. Not a crisis that made headlines or sparked congressional hearings. Just a quiet inconsistency in the mathematics. The kind of thing that keeps theoretical physicists awake at night while the rest of the world sleeps soundly. But this particular inconsistency would crack open a door to something vast. Something that would transform the observable universe from everything that exists into one bubble among infinite bubbles. Something that would make the 93 billion light-year sphere we call home look less like a cosmos and more like a single room in an infinite mansion. The problem was simple to state, difficult to solve. When you measure the geometry of space, and by the late 1970s astronomers had become quite good at this, you're asking a fundamental question. Does space curve back on itself like the surface of a sphere? Does it curve away like a saddle? Or does it extend flat like an infinite sheet of paper? Einstein's general relativity allows all three possibilities. The curvature depends on the total mass energy density of the universe. Too much density and gravity curves space into a closed sphere that will eventually collapse back on itself. Too little and space curves negatively expanding, forever thinning into cold infinity. Right in the middle at exactly the critical density space is flat, geometrically flat, Euclidean, the kind of space you learned about in high school where parallel lines never meet and triangles always have exactly 180 degrees. Measurements kept showing flatness, not approximate flatness. Remarkable, disturbing, shouldn't be possible flatness. The universe's density appeared to be within 1% of the critical value, which meant running the equations backward to the early universe that 1 second after the Big Bang, the density must have been fine-tuned to 1 part in 10 to the 15th power. By the time the universe was 1 trillionth of a second old, the fine-tuning required was 1 part in 10 to the 60th power. To understand what that means, imagine this. You're standing in Kansas flat plains stretching to every horizon. You place a coin on the ground. The coin must balance perfectly on its edge, not tilted even slightly. Balanced to a precision finer than atomic diameters. Now imagine doing that not once but a trillion, 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 trillion times in a row. Every single time the coin stays balanced. Perfect vertical equilibrium. That's the level of fine-tuning required for the universe to be as flat as observations indicated. Either the universe won an impossible lottery at the moment of creation or something flattened it. Something powerful enough to take whatever curvature existed initially and stretch it smooth. Alan Guth found that something. Guth was not famous in 1979. He was 32 years old, bouncing between postdoctoral positions, working on problems that interested almost nobody. He'd spent months thinking about magnetic monopoles, exotic particles predicted by grand unified theories but never observed. The lack of monopoles was a minor puzzle. Most physicists assumed they'd been diluted away somehow. But Guth kept circling back to one question: how do you dilute monopoles in the early universe without violating known physics? The answer came to him at 3 in the morning on December 10, 1979. What if space itself had grown? Not objects moving through space that was standard expansion already understood, but space itself inflating exponentially, doubling in volume every tiny fraction of a second, driven by some field stuck in a high-energy state. If space inflated fast enough, any magnetic monopoles would be spread so thin they'd be undetectable. Density would plummet. The universe would be mostly empty, with monopoles separated by distances far larger than the observable universe. But as Guth worked through the mathematics, he realized inflation solved more than the monopole problem. It solved flatness. Take a balloon, draw a triangle on it. The triangle's angles don't add up to 180 degrees because the surface is curved. But now inflate the balloon. Make it bigger. Keep inflating. By the time the balloon is the size of Earth, the triangle looks flat. The curvature is still there mathematically, but it's spread so thin you can't detect it. Inflate the balloon to the size of the observable universe. The curvature becomes utterly negligible. Space appears geometrically flat, not because it is fundamentally flat, but because inflation stretched any initial curvature beyond detection. The mathematics required space to inflate by at least a factor of 10 to the 26th power, a trillion times larger, in less than a trillionth of a second. This sounds absurd, and it is absurd by everyday standards. But quantum field theory permits it. If a field gets stuck in a false vacuum state, a high-energy configuration that's stable temporarily, but not permanently, the energy density of that field acts like anti-gravity. Instead of pulling space together, it pushes space apart, exponentially. Think of it as a compressed spring. The spring has stored energy. Release it suddenly, and that energy drives expansion. Except the spring is a quantum field pervading all of space, and the energy is enough to inflate the universe from smaller than an atom to larger than a grapefruit in a fraction of a second. When inflation ended, when the field finally dropped out of its false vacuum state, all that stored energy converted into particles and radiation. That conversion is what we call the Big Bang. Not the beginning of the universe, but the end of inflation. The moment when exponential growth stopped and normal expansion began. Guth wrote it all down, published the paper in 1981, called it Inflationary Universe, a possible solution to the horizon and flatness problems. Within months, physicists worldwide were working on inflation, refining it, fixing problems, exploring consequences, and one consequence stood out above all others. A consequence Guth hadn't anticipated. A consequence so strange that even he initially resisted it. Inflation might not stop everywhere at once. Andre Linde saw the flaw in Guth's original mechanism before most others did. Guth's version required the false vacuum to decay through quantum tunneling, like water suddenly freezing when temperature drops below 0 degrees. Bubbles of true vacuum would nucleate inside the false vacuum, expand, collide, and merge until the entire universe transitioned from inflation to normal expansion. But Linde realized this process was too violent. The bubble collisions would produce inhomogeneities, irregularities. The universe wouldn't be smooth and uniform. It would be choppy, scarred by phase transitions. Observations showed extreme smoothness. The cosmic microwave background varied by only 1 part in 100,000 across the entire sky. Bubble collisions couldn't produce that level of uniformity. Linde proposed a different mechanism. Instead of a single inflaton field stuck in false vacuum everywhere, suppose the field's value varied randomly across space due to quantum fluctuations. In regions where the field's value was high, inflation would continue. Space would keep doubling, expanding exponentially. In regions where quantum fluctuations dropped the field below a critical threshold, inflation would end. Normal expansion would take over. Matter and radiation would form. The regions where inflation ended became bubble universes. Each bubble would expand normally inside, filled with cooling radiation, eventually forming atoms, stars, galaxies. But outside the bubbles, in the regions where the field remained high, inflation would continue. Forever. Those inflating regions would grow faster than new bubbles could form within them. Imagine an infinite ocean constantly boiling. Bubbles form continuously, but the water volume doubles every second. Bubbles never merge because they're always separated by exponentially growing water. Each bubble is causally disconnected from others. Light can't travel between them. The inflating space expands faster than light can cross it. Each bubble is, for all practical purposes, a separate universe. This is eternal inflation. Linde published the idea in 1983. The reaction was skepticism mixed with fascination. The mathematics worked. Eternal inflation seemed to be a natural consequence of the simplest inflation models. You didn't need to fine-tune parameters to avoid it. If inflation started, it was hard to make it stop everywhere. But it raised an immediate objection. If eternal inflation is correct, we can never observe other bubbles. They're beyond our cosmic horizon, forever. So how is this science rather than speculation? Linde's answer was patient. Science makes testable predictions. Eternal inflation predicts specific patterns in the cosmic microwave background, specific relationships between density fluctuations at different scales, specific statistical properties. If those predictions matched observations, it wouldn't prove eternal inflation conclusively, but it would support the model. And if the predictions failed, the model would be ruled out. That's how science works. You can't prove a theory absolutely. You can only test its predictions and see if reality matches. For 30 years, Lindy refined the mathematics, built more sophisticated models, explored different inflaton potentials, waited for technology to advance enough to test the predictions. And in 2013, the Planck satellite delivered data precise enough to check. Stephen Feeney didn't set out to prove the multiverse exists. He was a graduate student at University College London working on cosmological data analysis. But he had an idea. If eternal inflation is real, and if bubble universes form continuously in eternally inflating space, then occasionally two bubbles might nucleate close together. Before expansion pushed them apart completely, their boundaries might touch. A collision between bubble universes would be catastrophic. Two different vacuum states meeting at light speed. The boundary would release enormous energy, far more than any particle collision at CERN spread across billions of light years. That energy would leave an imprint on the cosmic microwave background, a circular pattern, like throwing a stone into a still pond and watching ripples spread in perfect circles. If our bubble universe collided with a neighboring bubble billions of years ago, we should see the mark, a circular region on the sky where temperature fluctuations show specific patterns. Concentric rings, temperature variations correlated in ways that random quantum fluctuations alone couldn't produce. Feeney wrote algorithms to search for such patterns in Planck data. The satellite had spent 4 years mapping the microwave background with unprecedented precision. Temperature variations measured to millionths of a degree. Statistical properties analyzed across millions of data points. Most patterns in the data are noise. Random fluctuations from quantum uncertainty in the early universe stretched to cosmic scales by inflation. You expect temperature to vary from point to point, but the variations should be statistically uniform. No preferred locations, no geometric structure. Feeney searched for exceptions. He found 4 candidates. 4 circular patterns, each several billion light years across, with temperature correlations matching theoretical predictions for bubble collisions almost exactly. The probability of such patterns arising from random chance was low, not impossible, but low enough to be interesting. Other research teams jumped on the data. Some found additional candidates, as many as 30 potential collision signatures. Others argued the patterns were statistical flukes. When you search billions of data points, you're guaranteed to find some patterns by pure chance. The question is whether these particular patterns are more significant than chance allows. As of 2026, the debate continues. No consensus. The evidence is suggestive, but not conclusive. Some models of eternal inflation predict more collision signatures than observed. Others predict fewer. The statistical significance depends on assumptions about how you count patterns and how you define unusual. But here's what matters. The search is ongoing. New satellites are planned. Better statistical methods are being developed. The question is answerable in principle. We're not arguing about angels on pinheads. We're arguing about temperature patterns in microwave radiation, and those patterns either match predictions or they don't. That's science. Messy, uncertain, filled with disagreement and competing interpretations, but ultimately empirical, grounded in observation. And while the debate over collision signatures continues, another piece of evidence emerged. Indirect but powerful. Evidence from the most successful theory in physics, quantum mechanics. Specifically from the way quantum mechanics describes vacuum states. String theory began as an attempt to describe fundamental particles. Instead of point-like objects, what if particles were tiny vibrating strings? Different vibration patterns would correspond to different particles. Electrons, quarks, photons, all just different notes played on cosmic strings. The mathematics was beautiful. It unified quantum mechanics and gravity, something Einstein had tried and failed to do. It explained particle properties that seemed arbitrary in other theories. It suggested extra dimensions beyond the familiar 3 of space and 1 of time. But it had a problem. The equations didn't have one solution. They had approximately 10 to the 500th power solutions. Each solution corresponded to a different vacuum state, a different configuration of fields and forces, a different set of physical constants, strength of gravity, mass of the electron, charge of the proton, cosmological constant. In the 1980s, physicists hoped to find a unique solution, some deep principle that would select one vacuum state as correct and rule out all others. They searched for decades, found nothing. The landscape of possible vacuum states remained vast with no apparent mechanism to choose among them. Then in the early 2000s, Leonard Susskind proposed a radical solution. Don't choose. Accept the landscape. All those vacuum states are real. Each one realized somewhere in the eternal multiverse. Here's how it works. Eternal inflation constantly produces bubble universes. Each bubble nucleates from inflating space when quantum fluctuations drop the inflatant field below a threshold. As the bubble forms, fields settle into vacuum states. But which vacuum state? That depends on local conditions during nucleation. Quantum fluctuations, random variations, case at microscopic scales. With 10 to the 500th power possible vacuum states and infinite bubbles forming eternally, every vacuum state gets realized. Many times, infinitely many times, most vacuum states are sterile, hostile to complexity. In some, the cosmological constant is huge. Space expands so fast that matter never clumps into galaxies. No stars, no planets, no chemistry, just dilute gas spreading forever. In others, the strong nuclear force is too weak. Protons decay, atomic nuclei can't hold together. No stable atoms, no periodic table, no structures larger than individual particles. In still others, electrons are too heavy or too light. Chemical bonds don't form, or they form too readily, locking everything into rigid crystals. No liquid water, no carbon chemistry, no DNA. The vast majority of possible universes are dead on arrival, stillborn, incapable of supporting the kind of long-lived complex structures necessary for anything we'd recognize as interesting. But some, a tiny, tiny fraction, have parameters just right. Cosmological constant, small enough that galaxies form, but large enough to avoid recollapse. Strong force, strong enough to bind nuclei but weak enough to allow variety. Electromagnetic force balanced perfectly to permit chemistry. We're in one of those bubbles. Not because we're special, because consciousness can only arise in bubbles where the physics permits consciousness. This is the anthropic principle, not a fundamental law, a selection effect. Fish always find themselves in water, not because water is the only environment in the universe, but because fish die everywhere else. We find ourselves in a life-permitting bubble not because life-permitting bubbles are common, but because we couldn't exist in the sterile ones. Some physicists hate this reasoning. It feels like giving up on deeper explanation, like saying things are this way because if they weren't, we wouldn't be here to ask. It lacks the elegance of a unique mathematical solution. But if eternal inflation is correct, and if the string landscape is real, then anthropic reasoning isn't lazy thinking. It's acknowledging reality. Infinite bubbles with random vacuum states guarantee that all possibilities are realized. We observe life-permitting constants not because they're fundamental, but because we're selected from the subset of bubbles where observation is possible. And this has testable consequences. If our vacuum state is randomly selected from life-permitting options, we should expect to find ourselves in a typical life-permitting bubble. Not the most extreme, not the most finely tuned, somewhere in the middle of the probability distribution. The cosmological constant provides a test. It's incredibly small, about 10 to the minus 123rd power in natural units, but not zero. Why such a specific value? Anthropic reasoning suggests smaller values would permit more galaxies, more stars, more opportunities for life. But as you make the cosmological constant smaller, other factors change. Galaxy formation depends on balancing expansion against gravitational collapse. Too small a cosmological constant and you get different problems. Steven Weinberg calculated in 1987 that if you want galaxies to form, the cosmological constant must be smaller than a critical value. Larger and expansion overwhelms gravity too quickly. No structure forms that critical value, about 10 to the minus 120th power. The observed value is right at the edge, not the smallest possible, not the largest possible, right where you'd expect if you were randomly selected from a distribution of life-permitting bubbles. This doesn't prove the multiverse, but it's consistent with it, and it explains something that otherwise seems impossibly fine-tuned. The alternative is to believe our bubble universe won a cosmic lottery, that out of all possible vacuum states, we happen to get one of the infinitesimally rare life-permitting configurations by pure chance. Once, uniquely. Or you accept that the lottery was run infinite times. Every ticket eventually wins. We're in a winning bubble not because winning is likely, but because infinity guarantees all outcomes. That's the landscape argument, and it connects directly to something even stranger. Because if eternal inflation produces infinite bubbles, and if each bubble can have different physics, Then the question becomes, what defines the boundary between bubbles? What is a bubble fundamentally? The answer comes from black holes. Jacob Bekenstein was a graduate student in 1972 when he made a suggestion that his advisor John Wheeler thought was crazy. Black holes have entropy. Entropy measures disorder, information, the number of different microscopic configurations that produce the same macroscopic state. High entropy means many possibilities. Low entropy means few. Thermodynamics says entropy always increases. Systems evolve from order to disorder. Broken eggs don't spontaneously reassemble. Heat flows from hot to cold, never the reverse. But black holes seem to violate this. Throw matter into a black hole, and the matter's entropy vanishes, disappears beyond the event horizon. Total entropy of the universe decreases. Unless, and this was Bekenstein's radical suggestion, black holes themselves have entropy. Entropy that increases when matter falls in keeping total entropy constant or growing. Wheeler thought this was absurd. Black holes are solutions to Einstein's equations. Pure geometry. How can geometry have entropy? But Bekenstein worked out the mathematics. If black holes have temperature, and Stephen Hawking would prove in 1974 that they do, then thermodynamics requires they have entropy. The formula related entropy to the surface area of the event horizon, not volume, area. For normal matter, entropy scales with volume. Double the volume, double the entropy. More space means more possible arrangements of atoms. Black holes break this rule. Their entropy is proportional to surface area, specifically area divided by 4 times the Planck area, the smallest meaningful unit of area in quantum gravity. This was bizarre. A black hole's information content is determined by its 2-dimensional surface, not its 3-dimensional interior. It's as if everything about the interior, every particle that fell in every quantum state, every bit of information is somehow encoded on the event horizon. Like a hologram encodes 3-dimensional images in 2-dimensional interference patterns. Gerard de Hooft and Leonard Susskind took this observation seriously in the 1990s. They proposed the holographic principle: the maximum amount of information in any region of space is determined by the area of its boundary, not its volume. This wasn't just true for black holes. It was a general principle of quantum gravity. 3-dimensional space might not be fundamental. It might emerge from information encoded on 2-dimensional surfaces. You think you're moving through 3-dimensional space, but fundamentally you might be information on a 2-dimensional boundary experiencing the illusion of depth. Juan Maldacena proved this in 1997. Not for our universe exactly, but for a specific type of spacetime called anti-de Sitter space. He showed that everything happening in 5-dimensional ADS space can be completely described by a 4-dimensional quantum field theory on the boundary. Not approximately, exactly. Every event in the interior has a corresponding description on the surface. The 5-dimensional universe is a hologram projected from 4-dimensional information. This ADS/CFT correspondence became the most important result in theoretical physics of the 1990s. Within a year, it was the most cited paper in the field. Because if holography works for anti-de Sitter space, maybe it works generally. Maybe our universe de Sitter space with positive cosmological constant also has a holographic description. Apply this to the cosmic horizon. The cosmic horizon is the sphere surrounding you 46 billion light years in radius beyond which you cannot see, because light hasn't had time to reach you. It's an observational boundary, the edge of your accessible universe. But if the holographic principle applies, it's more than that. It's an information boundary. All information about everything inside the observable universe, every galaxy, star, planet, atom, quantum state thought you've ever had might be encoded on that distant 2-dimensional surface. The cosmic horizon as a holographic screen. And the 3-dimensional space you experience, emergent, derived, a projection from boundary data. You're not moving through pre-existing space. Space is being computed from information on the horizon, every moment, continuously. Your experience of depth, of volume, of moving from here to there, it's all holographic projection. This sounds like science fiction, but the mathematics is rigorous. A DS/CFT proves it works in specific cases. The question is whether it generalizes, and it connects to eternal inflation in a profound way. If bubble universes are defined by regions where inflation ended, then the boundary of a bubble isn't arbitrary. It's where the inflating field dropped below a critical value, where vacuum states transition from false to true, where space-time changed character. That boundary might be a holographic screen. Information about the bubble's interior encoded on its surface. The bubble's physics, its vacuum state, its constants, its structure determined by boundary data. In this picture, different bubbles aren't just regions with different physics. They're different holographic projections, different computations from different boundary information. And here's the deepest connection. If reality is holographic and if observation participates in collapsing quantum superpositions, then the act of observation isn't separate from reality. It's reading the hologram, computing definite states from boundary information. Consciousness becomes the process by which the hologram is actualized. Possibilities become realities. The wave function collapses. Three-dimensional experience emerges from two-dimensional encoding. You're not just in the universe. You're how the universe computes itself into definiteness. The double-slit experiment has been called the central mystery of quantum mechanics. Richard Feynman said it contains the only mystery of quantum theory. Everything else, he claimed, is just elaboration. Here's what happens. You shoot electrons one at a time through a barrier with two narrow slits. Behind the barrier, a detector screen records where each electron hits. If electrons were simple particles, you'd expect two bright bands on the screen. One behind each slit. Electrons go through one slit or the other like bullets through windows. But that's not what happens. Instead, you get an interference pattern. Multiple bands of light and dark, areas where electrons hit frequently alternating with areas where electrons never hit. The pattern looks exactly like what you'd get if waves passed through both slits and interfered with themselves. Constructive interference where waves align, destructive interference where they cancel. Each electron apparently passes through both slits simultaneously. It exists in a superposition of paths. The wave function describing the electron includes components going through each slit. Those components interfere. The interference determines where the electron is likely to hit the detector. This is strange but acceptable. Electrons have wave-like properties. Fine, but now place detectors at the slits to see which one each electron uses. Suddenly, the interference pattern vanishes. You get two simple bands. Each electron goes through one slit or the other. No superposition, no interference. The act of measurement changes the outcome. Not because the detector physically disturbs the electron, you can make the detector arbitrarily gentle, but because measurement forces the electron to choose, to collapse from superposition into a definite state. Before measurement, electron in both slits wave function spread across both paths. After measurement, electron in one slit wave function collapse to a single path. This isn't just about electrons. It's fundamental to quantum mechanics. Every quantum system exists in superposition until observed. Position, momentum, spin, energy, all undefined until measurement forces a choice. Niels Bohr argued that this is how reality works. Observation creates definiteness. Before measurement, asking which slit did the electron pass through is meaningless. Not because we don't know, but because there's no fact of the matter. Reality doesn't have definite properties until forced to by observation. Einstein rejected this. He believed in an objective reality existing independent of observation. Quantum mechanics might be incomplete, he argued, but surely electrons actually pass through one slit or the other even if we don't look. Decades of experiments have sided with Bohr. Quantum mechanics doesn't just describe our knowledge. It describes reality. And reality is fuzzy, probabilistic, undefined until observation forces specificity. John Wheeler pushed this further with delayed choice experiments. Imagine light from a distant quasar passing a massive galaxy. Gravity bends light. The quasar's photon can travel around either side. Two paths. Call them left and right. The photon began its journey billions of years ago. It's already passed the galaxy, already committed to one path or the other. Or so classical intuition suggests. Now set up a detector on Earth. You can configure it two ways. Either measure which path the photon took, force it to be definite, traveling left or right, or don't measure path. Instead, look for interference as if the photon took both paths simultaneously. Wheeler's insight: you can decide which measurement to make after the photon has already passed the galaxy, after it's been traveling for billions of years. Your choice now determines whether it took one path or both paths billions of years ago. Experiments confirm this. The photon's past is undefined until you measure it. Your measurement now affects what happened billions of years earlier. Reality doesn't just lack definiteness in the present until measured. Measurement reaches backward, forcing the past itself into definiteness. Apply this to cosmology. The early universe was small, quantum scale. Everything was governed by quantum mechanics. Superposition uncertainty, probabilistic wave functions. Before observation, the early universe existed in superposition of all possible configurations, all possible density fluctuations, all possible initial conditions. As the universe expanded and cooled, structures formed: atoms, stars, galaxies. Eventually observers, conscious beings capable of measurement. And in the act of observation, looking at stars, mapping galaxies, measuring the cosmic microwave background, those observers collapsed the wave function, forced the early universe's superposition into definiteness. The past became real through observation in the present. This sounds insane, but it's what quantum mechanics predicts. Wheeler called it the participatory universe. Observers don't just passively receive information about reality. They participate in creating definite reality from quantum possibility. Now consider regions beyond the cosmic horizon. Those regions are unobservable, not because they're too far away in some trivial sense, but because light from them hasn't reached us. We have not and cannot measure them. If quantum mechanics applies, and it must given that quantum mechanics governs everything at fundamental scales, then unobserved regions might not be in definite states. Not we don't know what's there, but there is no definite what's there. Beyond the horizon, quantum superposition, all possible configurations overlapping, density fluctuations in all possible patterns, matter in all possible arrangements, reality undefined, waiting for observation to collapse possibilities into actualities. The observable universe isn't just what we can see. It might be the only region where reality has crystallized into definiteness, where observation has occurred, where the wave function has collapsed. And as cosmic expansion continues, more regions cross into observability. Light from previously unreachable areas finally reaches us. We observe them for the first time. And in that moment, the moment of first observation, those regions transition from quantum superposition into classical definiteness, from all possible states to this specific state. We're not discovering pre-existing galaxies beyond the horizon. We're collapsing quantum superposition, actualizing one configuration out of infinite possibilities. This is where holography, quantum mechanics, and eternal inflation converge into a single picture. Eternal inflation produces bubbles. Each bubble is a region where inflation ended and normal expansion began. The boundary of a bubble, the cosmic horizon, encodes all information about the interior. The holographic principle says volume reality emerges from boundary information. Quantum mechanics says unobserved systems exist in superposition. Eternal inflation says space beyond our bubble is still inflating, possibly an undefined state. Put it together, our observable universe is a bubble where quantum superposition has collapsed into definiteness through the act of observation. The cosmic horizon is a holographic boundary encoding information. Beyond the boundary, either inflating space in quantum superposition, or other bubbles with their own holographic boundaries, or computational substrate running this simulation. You are not passively observing a pre-existing universe. You are participating in computing definite reality from quantum possibility, reading the hologram, collapsing the wave function, actualizing this specific configuration of matter and energy from infinite potential configurations. And this leads to the final, most vertiginous possibility. What if the entire structure, the multiverse, the holographic boundaries, the quantum superpositions, the act of observation is itself computation? What if reality is information processing? In 2003, a philosopher named Nick Bostrom published a paper that went viral among physicists, computer scientists, and late-night dorm room debaters. He presented a simple logical argument: 3 possibilities, at least one of which must be true. First possibility: nearly all civilizations at humanity's current level of development go extinct before achieving the computational power to run high-fidelity ancestor simulations, detailed simulations of conscious beings living in realistic universes. Second possibility: civilizations that survive to develop such technology overwhelmingly choose not to run simulations, perhaps for ethical reasons. Third possibility: we are almost certainly living in a simulation. The logic is straightforward. If civilizations survive long enough to develop simulation technology, and if they have any interest in running simulations, they'll run many, thousands, millions. The computational resources available to an advanced civilization are vast. Running detailed simulations of conscious beings would be trivial for technology only a few centuries ahead of ours. If many simulations run, the number of simulated consciousnesses will vastly outnumber biological ones, by factors of millions or billions or more, which means any given conscious entity like you is statistically more likely to be simulated than original. Like a lottery in reverse. Most tickets win, This sounds like science fiction. But when physicists started examining this argument seriously, they looked for evidence, signs that our universe might be computational. They found several suggestive features. First, fundamental limits to measurement precision. Quantum mechanics imposes hard limits. You cannot measure position and momentum simultaneously with arbitrary precision. The Heisenberg uncertainty principle prevents it, not because instruments are imperfect, but because reality itself is fuzzy at small scales. Similarly, space-time itself has minimum scales. The Planck length 10 to the minus 35th power meters represents the smallest meaningful distance. Below that, quantum fluctuations make the concept of distance break down. The Planck time 10 to the minus 43rd power seconds is the smallest meaningful time interval. These look like pixelation, like a minimum resolution, like the universe renders reality at its specific scales and no finer exactly as a simulation would to conserve computational resources. Second, observer-dependent rendering. Quantum superposition until measurement. This is precisely how an optimized simulation would work. Don't compute what's not observed. Keep unobserved regions in compressed state superposition and only calculate definite values when observation demands it. Video games do this. They don't render the entire game world constantly. They render what the player sees. Everything else exists in low resolution, placeholder state until needed. The universe does the same. Quantum systems remain in superposition, a computationally efficient state representing all possibilities simultaneously, until observation requires computing a specific outcome. Third, mathematical structure. Physical laws can be written as equations, relatively simple equations considering the complexity they generate. Einstein's field equations fit on a t-shirt. The Schrödinger equation is one line. Maxwell's equations for electromagnetism, 4 equations total. From these simple rules emerges all the complexity of chemistry, biology, weather galaxies, consciousness. Enormous diversity from compact foundations. This resembles code, elegant algorithms that generate complexity through iteration. Conway's game of life creates intricate patterns from 4 simple rules. Cellular automata produce endless variety from minimal programming. If the universe is a simulation, its laws would be algorithms, and algorithms are mathematics executed. Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematics describe physical reality so perfectly? If reality is computation, mathematics isn't mysteriously effective. It's the language of computation. The universe isn't described by math. It is math being executed. Max Tegmark takes this to its logical conclusion. He argues the universe doesn't just follow mathematical laws. The universe is a mathematical structure. Physical reality is mathematics. What we call matter and energy and space-time are all just mathematical objects, solutions to equations existing in some platonic realm of pure mathematics. And if all mathematical structures exist, then every possible universe exists. Every consistent set of equations defines a universe. Somewhere in the space of all possible mathematics, every configuration is realized. This is Tegmark's Level 4 multiverse, beyond Level 1 regions outside our horizon. Beyond Level 2, other bubbles from eternal inflation. Beyond Level 3, parallel branches from quantum measurement. Level 4 proposes that every possible mathematical structure exists as a universe. We're in one such structure, one set of equations, one configuration of mathematical rules. But infinite others exist. Universes with different dimensionality, different symmetries, different fundamental constants, different mathematics entirely. And here's where it loops back to simulation. If the universe is mathematics, and if mathematics can be computed, then advanced civilizations could simulate universes by computing mathematical structures. They don't need to build physical universes. They run the equations. The simulation is the universe. And if they run the equations on computational substrate, whatever serves as their computers, then the simulated universe exists on that substrate. The substrate is in some base reality with its own physics, and the simulation runs within it, following different physics, different rules, experiencing different time. From inside the simulation, you can't detect the substrate directly. You experience the simulated physics. You measure the simulated constants. You observe the simulated spacetime. But certain features might hint at the computational nature. The holographic principle, for instance. If reality is fundamentally two-dimensional information projected into three-dimensional experience, that's exactly what you'd expect from efficient computation. Store data on two-dimensional arrays. Compute three-dimensional space from that data. Minimize redundancy, or quantum mechanics. Superposition is computationally efficient. You don't calculate every particle's exact state every instant. You calculate probability distributions. Only when measurement occurs do you compute specific values. This conserves resources dramatically. Or the cosmic horizon, the boundary beyond which you cannot observe. From a computational perspective, that's the edge of what needs to be rendered. Beyond the horizon, the simulation can use placeholder values, low-resolution approximations, or simply not compute at all. No observer can check. Different bubble universes in eternal inflation. Different simulation instances running different parameter sets, all executing on the same substrate in base reality. The string landscape of vacuum states and different initial conditions for different simulations. Each one a different experiment in physics. It all fits, disturbingly well. But here's the question that keeps philosophers awake. If we're in a simulation, what about the base reality running the simulation? Is base reality also a simulation? And if so, what runs that simulations all the way down? Or is there an ultimate base reality, the foundation layer, the original universe, where the first civilization arose and built the first simulation? And if there is such a base reality, how do we know we're not it? Maybe we're not in a simulation. Maybe we're the original, the base layer, the foundation on which future civilizations will build simulations of their own. Or maybe the distinction doesn't matter, but John Wheeler saw something deeper. In his final years at Princeton, working into his 90s, Wheeler synthesized quantum mechanics, cosmology, and information theory into a single principle. He called it it from bit. Every physical thing, every it derives from informational choices. Binary yes or no questions, bits. Not because reality is made of information metaphorically, but because physics is information processing. Observation asks a question. Which slit? What position, what energy of reality answers? The answer creates the it, the physical thing, the definite state. No observation, no question, then no answer. No it. Only superposition, with all possibilities overlaid. Wheeler realized the universe is a self-referential loop. It observes itself through consciousness, through measurement, through asking questions, and in answering its own questions, it creates itself, continuously, moment by moment. This is not poetry. This is the mathematical structure emerging from quantum mechanics plus holography plus observation. If holography is correct, volume reality emerges from boundary information. If quantum mechanics is correct, observation collapses superposition into definiteness. If eternal inflation is correct, our bubble is one computation among infinite computations. If simulation hypothesis is viable, reality is mathematical execution on substrate. Put them all together and you get Wheeler's insight. Reality is self-creation through self-observation. The universe asks itself what it is and becomes definite through the asking. You're not in the loop, you are the loop. The universe asking itself what it is and actualizing through the question. This is the deepest pattern, the metastructure underlying everything we've discussed. Inflation creates bubbles. Bubbles have holographic boundaries. Boundaries encode information. Information exists in superposition until observed. Observation is consciousness reading the hologram. Reading actualizes definite states from quantum possibilities. The circle closes. You are not separate from the universe. You are not watching from outside. You are the mechanism by which undefined possibility crystallizes into definite actuality. You are the universe computing itself, observing itself, knowing itself. Carl Sagan was right, but now you understand why. The atoms in your body were forged in stellar cores billions of years ago. Carbon from red giants, oxygen from supernovae, nitrogen from cosmic rays. Every element heavier than helium synthesized in nuclear furnaces and scattered across space when those furnaces died. Those atoms drifted, coalesced into molecular clouds, collapsed under gravity into new stars, formed planets from leftover debris. On at least one planet, chemistry became complex enough for replication. Self-copying molecules, natural selection, evolution. Evolution produced nervous systems. Nervous systems developed consciousness. Consciousness asked questions, built instruments, discovered that the stars it watched were the wombs where its atoms were born. You are the universe, not metaphorically, literally, rearranged, conscious, curious. And if holography is correct, you're not just made of the universe. You're the universe reading its own holographic encoding, computing three-dimensional experience from two-dimensional boundary information. collapsing quantum possibilities into classical actualities through the act of observation. You're the mechanism by which reality becomes definite. The cosmic horizon isn't where the universe ends. It's where your frame of awareness ends. The boundary of what you've computed, what you've rendered, what you've actualized from quantum possibility. Beyond that boundary lies more. Infinite more. Eternal inflation generating endless bubbles. Other vacuum states. Other physics. Other computations running on the same substrate. You'll never see it directly. Light hasn't reached you. Dark energy ensures it never will. The horizon is absolute. But you know it's there. Not through faith, through mathematics, through observation, through the patient work of scientists over a century. Edwin Hubble at his telescope night after night mapping galactic distances. George Gamow scribbling thermodynamic predictions on napkins. Arno Penzias and Robert Wilson cleaning pigeon droppings and finding creation's echo. Alan Guth lying sleepless, realizing space could grow. Andre Linde refining eternal inflation through decades of patient calculation. Juan Maldacena proving that volume emerges from boundary information. John Wheeler showing that reality is self-referential observation. Each built on their predecessors. Each pushed understanding one step further into terrain beyond common sense. And now you stand at the edge of their collective achievement, looking out at a cosmos larger and stranger than anyone imagined. The observable universe, 93 billion light-years across. One bubble among possibly infinite bubbles. One computation among infinite computations. One holographic projection among endless projections. And you temporary arrangement of atoms, brief spike of consciousness, localized computation in cosmic substrate, you understand. That's not diminishment, that's triumph. In the cosmic war between mystery and understanding, understanding is winning slowly, incrementally, through patience and rigor and generations of accumulated effort, but winning, and you're here for it. Conscious during the century when humanity discovered it's inside something much bigger. That's not loss of significance, that's expansion of wonder. The journey continues. Raymond Davis was 74 years old when he won the Nobel Prize in Physics. He'd spent 30 years, the majority of his professional life, staring at a tank of cleaning fluid. 600 tons of perchloroethylene buried 1 mile underground in the Homestake gold mine in South Dakota, waiting for neutrinos. Neutrinos from the sun, ghostly particles produced by nuclear fusion in the solar core streaming outward at the speed of light, passing through the Earth as if it weren't there. Through rock, through metal, through human bodies, through everything. 10 trillion neutrinos pass through your thumbnail every second. You never feel them. They interact with matter so weakly that a neutrino could pass through a light year of solid lead and have a 50-50 chance of making it through without hitting anything. Davis built his detector in the 1960s based on a prediction. If the sun runs on fusion, and it must because nothing else could power it for billions of years, then fusion produces neutrinos. Lots of them. And occasionally, very occasionally, a neutrino would hit a chlorine atom in the cleaning fluid and convert it to argon. The math predicted he should capture about 30 neutrinos per month. He caught 10. For 3 decades, the numbers didn't match. 1/3 the expected rate. Colleagues suggested errors, problems with the detector, mistakes in calculation. Maybe the sun wasn't powered by fusion after all. Maybe the entire theory of stellar nucleosynthesis was wrong. Davis kept measuring, kept refining, kept checking. He was right. The sun was right. The deficit was real. The solution came from elsewhere. Neutrinos change flavor. They oscillate between 3 types as they travel. The sun produces one type. Davis's detector only caught one type. But during the 8-minute journey from solar core to Earth, neutrinos transformed. 2/3 became a different flavor, invisible to his detector. When physicists finally understood neutrino oscillation in the 1990s, Davis's 30 years of patient observation became vindicated. He'd measured exactly what he should have measured. The deficit was the discovery. In 2002, at age 78, he received the Nobel Prize. 30 years, 1 tank of fluid, 1 simple measurement, repeated thousands of times. Through budget cuts and skepticism, and the quiet gnawing doubt that maybe, just maybe, everyone else was right, and he was wasting his life on a broken experiment. But he wasn't. He was doing science the way science works, not through sudden flashes of genius, through patience, through rigorous methodology, through refusing to quit when the data doesn't match expectations. This is the story of cosmology. Not just the theoretical breakthroughs, Guth's inflation, Lindy's eternal bubbles, Maldacena's holography, Wheeler's self-referential loop, But the experimental verification, the decades spent building instruments, the years analyzing data, the patient accumulation of evidence that turns speculation into knowledge, and the honest acknowledgement at every step of what we know and what we don't. The Planck satellite launched on May 14, 2009 from French Guiana, a European Space Agency mission designed to map the cosmic microwave background with unprecedented precision. It carried two instruments: low-frequency instrument measuring long wavelength microwaves, high-frequency instrument measuring short wavelengths. Together, they scanned the entire sky, measuring temperature variations in the ancient light to millionths of a degree. The mission was planned for 15 months. It operated for 4 years. The satellite itself was relatively simple. A telescope just over 1 meter wide. Detectors cooled to 1/10 of a degree above absolute zero to reduce noise. Solar panels for power. A spin-stabilized orbit at the second Lagrange point, where Earth's and Sun's gravity balance, keeping the satellite in stable position for observation. Simple in concept, staggeringly difficult in execution. Every component had to work perfectly. The detectors had to maintain extraordinary sensitivity while bathed in cosmic radiation. The cooling system had to function for years without maintenance. The data transmission had to send billions of measurements back to Earth without corruption. And it did. For 4 years, Planck mapped the sky over and over, building up signal through repetition, averaging out noise through statistics, slowly, painstakingly constructing the most detailed map of the early universe ever made. The data came down in 2013. Analysis took another 5 years. Why so long? Because cosmology is hard. You're not just measuring temperature. You're extracting information encoded in statistical patterns, correlations between different regions of sky, power spectra at different angular scales, signatures of primordial gravitational waves hidden in polarization patterns. Every analysis requires checking against systematic errors. Instrumental effects, foreground contamination from our galaxy, statistical flukes, selection bias. You run simulations, thousands of them, generating artificial universes with known properties, analyzing them the same way you analyze real data, checking whether your methods recover the input, refining when they don't. You compare different analysis pipelines. Independent teams working on the same data. If they get different results, you investigate. Find the discrepancy. Resolve it. Only after years of this meticulous work do you publish results. And even then you include error bars, confidence intervals, honest statements about uncertainties. The final Planck results published in 2018 represented 9 years from launch to completion. 9 years for a mission planned as 15 months. But the results were worth it. The universe is 13.8 billion years old, plus or minus 20 million years. Uncertainty less than 1%. Space is flat to within 0.4%, either exactly flat or so close that curvature is undetectable. Ordinary matter makes up 4.9% of total energy density. Dark matter, 26.8%. Dark energy, 68.3%. The cosmic microwave background has a temperature of 2.725 Kelvin, varying by 1 part in 100,000 across the sky. These aren't guesses, they're measurements, precise, rigorous, checked, and double-checked by independent teams across the world. And they confirm inflation's predictions almost exactly. The pattern of temperature fluctuations matches what you'd expect from quantum fluctuations during inflation, stretched to cosmic scales. The statistical properties fit theoretical models to remarkable precision. Does this prove inflation happened? No. Science doesn't prove theories. It tests predictions. Inflation's predictions match observations. Other theories don't match as well. So we provisionally accept inflation as our best current model while remaining open to better models if data changes. That's intellectual honesty. That's how science works. And it requires patience. 9 years for Planck, decades for earlier missions, COBE in the 1990s, WMAP in the 2000s. Generations of scientists building on predecessors' work. The cosmic microwave background was predicted in 1948, discovered accidentally in 1964, mapped crudely by COBE in 1992, mapped precisely by WMAP in 2003, mapped definitively by Planck in 2013. 65 years from prediction to detailed confirmation. Multiple human lifetimes. Careers beginning and ending. Students becoming professors, becoming emeriti. But the truth emerged, slowly, patiently, through accumulated effort. And the work continues. Deep in Antarctica, at the geographic South Pole, sits a telescope designed to detect something that might not exist. The BICEP array. Background imaging of cosmic extragalactic polarization. Multiple telescopes working together staring at the same patch of sky for years, looking for a specific pattern in the cosmic microwave background. They're searching for B-mode polarization. Light is electromagnetic radiation. It oscillates. The direction of oscillation is called polarization. The cosmic microwave background is polarized. Temperature fluctuations create patterns of polarization across the sky. Most polarization is E-mode. Gradient patterns. These arise naturally from density fluctuations in the early universe. Planck mapped E-modes extensively. They're well understood. But inflation predicts another type B-mode. Curl patterns. These can only be produced by gravitational waves from the inflationary epoch. Ripples in space-time itself generated by the exponential expansion, leaving a characteristic swirl pattern in the microwave background's polarization. If you detect beam modes with the right characteristics, you've found direct evidence of inflation. Not just indirect evidence from density fluctuations, but a smoking gun. Proof that space-time underwent violent expansion in the first fraction of a second after the Big Bang. Multiple experiments are searching. BICEP at the South Pole, the Simons Observatory in Chile, future space missions like Lightbird. In 2014, BICEP announced a detection. Headlines worldwide. Gravitational waves from Big Bang detected. Evidence for inflation. Possible evidence for eternal inflation and the multiverse. Within months, the claim collapsed. The signal was contaminated by dust in our galaxy. Foreground emission that mimicked the B-mode pattern. After careful analysis combining BICEP data with Planck's dust maps, the gravitational wave signal disappeared. Statistical noise and galactic contamination, not primordial. This was not failure. This was science working correctly. You make a measurement. You announce it. Other teams check. If they find problems, you investigate. You refine. You correct. You publish updated results acknowledging the error. The BICEP team did exactly that. No defensiveness, no doubling down, just honest acknowledgement. We were wrong. The signal is dust, not gravitational waves. And then they built better instruments. Improve calibration. Develop better methods for separating foreground contamination from primordial signal. As of 2026, no confirmed B-mode detection from inflation. Upper limits keep improving. The signal, if it exists, is weaker than initially hoped. This constrains inflation models. Rules out the simplest versions that predict strong gravitational waves. But the search continues. Better instruments, longer observation times, more sophisticated analysis. Because if B-modes are detected, if gravitational waves from inflation are found, it will be one of the most important discoveries in the history of cosmology. Direct observation of quantum fluctuations in space-time itself. Evidence that space underwent exponential expansion. A window into physics at energy scales far beyond any particle accelerator. That's worth decades of effort. Worth careers spent staring at the South Pole sky. Worth the risk of never finding anything. Science isn't just about what you discover. It's about what you constrain. Negative results matter. If inflation doesn't produce strong gravitational waves, that tells us something important about which inflation models are correct. Every measurement refines understanding, even especially when it rules things out. And sometimes patience pays off spectacularly. On September 14, 2015, at 5:51 a.m., Eastern Time, gravitational waves from two colliding black holes passed through Earth. The waves had been traveling for 1.3 billion years. They stretched and compressed space by less than 1,000th the diameter of a proton. For 1/5 of a second, as the waves passed, every meter of space oscillated by 10 to the negative 18th power meters, undetectable by any instrument ever built. Except one, LIGO, the Laser Interferometer Gravitational Wave Observatory. Two facilities, one in Louisiana, one in Washington State, each containing L-shaped vacuum tubes 4 kilometers long. Lasers bounce along the tubes, and when gravitational waves pass through, they change the tube's lengths by infinitesimal amounts. The lasers detect the change through interference patterns. The precision required is insane. Measuring distance changes smaller than a proton's width across 4-kilometer baseline. Isolating the signal from seismic noise, thermal fluctuations, quantum uncertainty, truck traffic a mile away, ocean waves hitting the coast. LIGO was proposed in the 1960s, funded in the 1990s, built in the 2000s, upgraded through the 2010s. First detection, 2015. 55 years from concept to success. If you were 50 in 1990 when LIGO was funded, you were 75 by the time it detected gravitational waves. A quarter of your adult life spent waiting for vindication. That's patience on human scale, mirroring patience on cosmic scale. 55 years of skepticism, of budget fights, of technical challenges that seemed insurmountable, of preliminary runs detecting nothing, of colleagues saying it would never work. But it did work, because the scientists building it were patient, because they solved problems one by one, because they refined instruments until precision exceeded what seemed physically possible. The September 2015 detection was so clear, so obvious that analysts initially thought it was a test injection, fake data inserted to check whether the pipeline worked correctly. Only after confirming no test had been scheduled did they realize this is real. Two black holes 29 and 36 times the mass of the Sun orbited each other, spiraled inward, merged in a final cataclysmic collision that converted 3 solar masses worth of matter into pure gravitational radiation. The final burst of waves carried more power than all the stars in the observable universe combined. For 1/5 of a second, those two black holes outshone the entire cosmos. And LIGO heard it. A chirp, frequency increasing as the black holes spiraled faster, amplitude growing as they approached merger. Then silence as the combined black holes settled into stable configuration. The detection was announced in February 2016, press conference. Papers published simultaneously in physical review letters. Nobel Prize awarded in 2017. But LIGO didn't stop. As of 2026, they've detected over 90 gravitational wave events, black hole mergers, neutron-star collisions, each one revealing something about extreme physics, about how space-time behaves when gravity becomes overwhelmingly strong, and future detectors will do more. LISA Laser Interferometer Space Antenna will launch in the 2030s. 3 spacecraft in triangular formation, millions of kilometers apart, detecting gravitational waves from supermassive black holes from the early universe, possibly from cosmic strings or phase transitions in the first moments after the Big Bang. LISA might detect gravitational waves from inflation itself, primordial ripples in spacetime, the same signal BICEP searches for in microwave background polarization but detected directly rather than through electromagnetic imprints. If LISA finds them, we'll have heard the universe's birth cry, not metaphorically, literally. Gravitational waves are vibrations in space-time. Sound waves are vibrations in air. LISA will detect cosmic sound from the first instant of existence. That's what patience buys. 55 years from LIGO concept to detection, 70 years from concept to LISA launch. Multiple human generations working toward the same goal. And it's worth it. Because the alternative giving up, because the problem is hard, because results take decades, because you might not live to see success. That's not how progress happens. Progress happens through patience, through commitment, through refusal to quit when the easy path would be abandoning the search. Ray Davis, 30 years underground. LIGO team, 55 years from idea to detection. Planck mission, 9 years from launch to final results. BICEP array, still searching, JWST. 25 years from proposal to launch. These aren't stories of genius. They're stories of persistence, of methodical work, of showing up day after day, year after year, solving problems as they arise, refusing to accept that difficulty means impossibility. And that persistence has produced the most extraordinary map of reality humans have ever drawn. What we know now, the observable universe is 13.8 billion years old. Not approximately, not somewhere between 10 and 20 billion. 13.8 billion with uncertainty less than 1%. We know this from measuring cosmic expansion, from dating the oldest stars, from analyzing the cosmic microwave background. Multiple independent methods agree. Space is flat, either exactly flat extending infinitely or curved so slightly that the radius of curvature exceeds the observable universe by a factor of 250. We know this from measuring angles between distant objects, from analyzing how light travels through space, from mapping cosmic geometry with gravitational lensing. The universe is expanding, accelerating, driven by dark energy that makes up 68% of total energy density. We know this from observing distant supernovae, from measuring cosmic expansion rate at different epochs, from tracking how galaxy recession velocity increases with distance. Structure formed from quantum fluctuations. Tiny density variations in the early universe amplified by inflation grew through gravitational attraction into galaxies clusters, the cosmic web. We know this from mapping galaxy distribution, from simulating structure formation, from comparing predictions to observations across billions of light years. These aren't theories, they're measurements, tested repeatedly, confirmed by multiple independent methods, the foundation of modern cosmology. But here's what intellectual honesty requires. Acknowledging what we don't know. Dark energy's nature remains mysterious. Is it Einstein's cosmological constant vacuum energy inherent to empty space? Is it a dynamical field that changes over time? Is it a sign that general relativity breaks down at cosmic scales? We don't know. We have measurements showing dark energy exists and dominates cosmic dynamics, but we don't understand it fundamentally. Inflation explains cosmic flatness and uniformity beautifully, matches observations of structure formation, predicts patterns in the microwave background that we observe, but we don't know what drove it. The inflating field is hypothetical. We haven't detected it. We haven't measured its properties directly. Inflation is our best model. That doesn't mean it's proven. Eternal inflation follows mathematically from inflation's simplest versions. If inflation happened, it's hard to make it stop everywhere simultaneously. Eternal inflation seems natural, but observational evidence is indirect at best. Circular patterns in the microwave background are suggestive, not conclusive. Collision signatures from other bubbles remain disputed. The multiverse, other bubble universes with different physics, is implied by eternal inflation plus string theory's landscape. The logic is sound. The mathematics works, but by definition, other bubbles are unobservable. We can test whether our models are consistent. We can look for indirect evidence. We cannot directly confirm other universes exist. The holographic principle works mathematically in ADS space. Maldacena proved it rigorously. Whether it extends to our universe de Sitter space with positive cosmological constant remains conjecture. Reasonable conjecture, well motivated, but not proven. Simulation hypothesis is philosophically interesting. Bostrom's logic is sound, but it's unfalsifiable. If the simulation is perfect, no test can distinguish simulated from real. That makes it metaphysics, not physics. Interesting to contemplate. Impossible to prove or disprove. Wheeler's it from bit, the idea that reality is self-referential observation loop, is mathematically elegant. It synthesizes quantum mechanics, holography, and information theory beautifully. But whether it's a deep truth about nature or a compelling mathematical metaphor remains open. This is the honest state of cosmology in 2026. We know the observable universe's age, composition, geometry, expansion history. We have strong models for cosmic inflation, structure formation, the cosmic microwave background. We have indirect evidence suggesting the universe extends far beyond what we observe, possibly infinitely. But the deepest questions remain open. What is dark energy? What drove inflation? Does the multiverse exist? Is reality holographic? Are we simulated? Is observation fundamental to reality's structure? These questions aren't rhetorical. They're research programs, active investigations, experiments being built, data being analyzed, models being refined, and the answer to each question might be we'll never know for certain. Some truths might lie forever beyond observational reach. The cosmic horizon imposes hard limits. Quantum mechanics imposes fundamental uncertainties. Mathematics proves that some questions can't be answered from within the system asking them. But that doesn't mean stop trying. Because even if we never confirm the multiverse, the search teaches us about quantum field theory, general relativity, cosmological dynamics. Even if we never prove holography applies to our universe, the mathematics enriches understanding of quantum gravity. Even if we never resolve the simulation hypothesis contemplating, it sharpens thinking about consciousness, computation, the nature of reality. Science progresses through questions, not just answers, through pushing boundaries, through testing limits, through patient observation of phenomena at the edge of what's detectable. And sometimes more often than cynics expect, patience is rewarded. Right now, photons from a galaxy 10 billion light years away are entering Earth's atmosphere. They've been traveling since before the sun existed, before Earth formed, before anything in our solar system was more than dispersed atoms drifting through space. 10 billion years of journey, through expanding space, through the cosmic web, through intergalactic voids and galaxy clusters, and in 1 second they'll hit a telescope mirror in Hawaii, be focused, detected, recorded, added to humanity's map of the cosmos. That photon's journey, 10 billion years of travel, ends in a human discovery, a conscious acknowledgement, a moment of understanding, the universe speaking to itself across cosmic time. You are that conversation, that moment, that understanding. Space itself is expanding. Dark energy pushing galaxies apart. Right now in the room you're in, space is growing by about 1 millimeter per year. Too slow to notice. Too small to affect anything bound by electromagnetic or gravitational forces. But cumulative. Across cosmic distances, it dominates. Accelerating. Inexorable. And you know this, not because you feel it directly, not because it's obvious to common sense, but because scientists, generations of them, building on each other's work, measured it, calculated it, tested it repeatedly until uncertainty shrank to negligible levels. Edwin Hubble measuring galaxy redshifts one photographic plate at a time. George Gamow predicting microwave background radiation from thermodynamic reasoning. Arno Penzias and Robert Wilson finding it by accident while cleaning pigeon droppings. Alan Guth realizing at 3 in the morning that space could inflate exponentially. André Linde refining eternal inflation through 30 years of patient calculation. Saul Perlmutter coordinating teams across continents to photograph distant supernova, discovering acceleration. Juan Maldacena proving volume reality emerges from boundary information. John Wheeler showing that reality is self-referential observation. Ray Davis waiting 30 years in a South Dakota mine for neutrinos. LIGO team spending 55 years building detectors to hear gravitational waves. Each added one piece, each built on predecessors. Each pushed understanding one increment further into territory beyond direct perception. And now you stand at the culmination of their collective effort, knowing truths about reality that would have seemed like magic a century ago. You know the universe is expanding, accelerating, driven by mysterious dark energy. You know space is flat or nearly so, extending far beyond observable horizons. You know inflation likely happened, stretching quantum fluctuations to cosmic scales. You know structure formed from those fluctuations through gravitational collapse. You know the universe is 13.8 billion years old, composed mostly of dark matter and dark energy, with ordinary matter a small minority. You know or have strong reason to suspect that the observable universe might be one bubble among infinite bubbles in eternally inflating space. That other bubbles might have different physics. That reality might be holographic, with three-dimensional experience emerging from two-dimensional information. That observation participates in defining reality through quantum collapse. That the entire structure might be self-referential, the universe observing itself, creating itself through observation. These aren't wild speculations. They're the natural conclusions of mathematical models tested against observation. Provisional conclusions, uncertain in details, but supported by evidence accumulated through decades of patient work. And that knowledge changes nothing about your daily life and everything about your cosmic perspective. Carl Sagan died in 1996, age 62, from pneumonia following bone marrow disease. He never saw the Planck satellite's measurements confirming cosmic flatness. Never saw LIGO detect gravitational waves. Never saw JWST photograph galaxies from 400 million years after the Big Bang. But in his final book, published posthumously, he wrote about the cosmic perspective, about what it means to know you're made of star stuff, to understand you're the universe experiencing itself. He wrote, "We're a way for the cosmos to know itself." It's the most famous line he ever wrote, quoted endlessly, often dismissed as poetry, beautiful but vague. But after understanding inflation, eternal bubbles, holographic encoding quantum observation, Wheeler's self-referential loop, you see it's not vague at all. It's literally true. The atoms in your body were forged in stellar cores. Carbon from red giants, oxygen from supernova, nitrogen from cosmic ray interactions. Every element heavier than helium synthesized in nuclear furnaces and scattered across space when those furnaces died. Those atoms drifted, coalesced into molecular clouds, collapsed under gravity into new stars, formed planets from leftover debris. On at least one planet, chemistry became complex enough for replication. Self-copying molecules, natural selection, evolution. Evolution produced nervous systems. Nervous systems developed consciousness. Consciousness asked questions, built instruments, discovered that the stars it watched were the wombs where its atoms were born. You are the universe. Not metaphorically, literally, rearranged, conscious, curious. And if the holographic principle is correct, you're not just made of the universe. You're the universe reading its own holographic encoding. computing three-dimensional experience from two-dimensional boundary information, collapsing quantum possibilities into classical actualities through the act of observation. You're the mechanism by which reality becomes definite. Freeman Dyson, who died in 2020 at age 96, spent his final decades thinking about time without end, about whether consciousness could survive the heat death of the universe, about meaning in cosmic context. In one of his last interviews asked what it all means, he said, "The universe gave us 13.8 billion years to wake up. We woke up. That's enough. No cosmic purpose imposed from outside. No divine plan guaranteeing significance. Just local complexity arising from simple rules. Matter arranged into patterns capable of understanding their matter. And that consciousness emerging from cosmic evolution doesn't need external validation to be meaningful. The universe is vast, mostly empty, mostly cold, mostly dark. Stars outnumbered by void. Matter outweighed by dark energy. Observable universe possibly an infinitesimal fraction of total existence. And yet, on one planet, around one star, in one galaxy, among trillions, in one bubble, among possibly infinite bubbles, atoms woke up, built telescopes, detected microwaves from creation, measured cosmic expansion, inferred inflation, proposed multiverse, developed holographic principle, understood partially the structure of reality. Is the universe indifferent to this? Probably. The universe is not a person. It doesn't care. Indifference is not cruelty. It's just physics following rules. But you're not indifferent. You care. You question. You discover. And that caring, that curiosity, that drive to understand, that's not separate from the universe. That's the universe caring about itself through you. In the cosmic struggle between entropy and complexity, complexity won. Locally, temporarily, but really, against the tide of disorder, pockets of order emerge, stars fusing hydrogen, planets forming stable orbits, chemistry building molecules, molecules building cells, cells building brains, brains building civilization, civilization building science, and science discovering that the tiny bubble of complexity we inhabit is nested inside something incomprehensibly larger. That discovery doesn't diminish you, it elevates you. Only something vast could produce consciousness capable of comprehending vastness. Only something complex could generate minds capable of understanding complexity. You're not a cosmic accident. You're a cosmic inevitability. Given enough time, enough space, enough random variation, matter arranges itself into patterns that think. And once thinking begins, it doesn't stop. It asks questions. It seeks answers. It pushes boundaries. The cosmic horizon limited ancient humans to Earth, then to solar system, then to galaxy, then to observable universe. Each expansion of horizon revealed more questions, deeper mysteries, stranger truths. And now we know or strongly suspect that even the observable universe is just one room in an infinite mansion, one bubble in eternal foam, one computation among infinite computations. We'll never observe most of it. The horizon is absolute. Dark energy ensures expansion carries distant regions beyond reach faster than light can travel. But we know it's there, through mathematics, through inference, through extending local physics to cosmic scales and seeing where the equations lead. That knowledge doesn't make life meaningless. It makes life remarkable. You exist during the cosmic instant when matter is arranged into stars and planets and consciousness. Before now, the universe was too hot, too simple. After now, trillions of years hence, it will be too cold, too dispersed. Right now is special. Not because the universe planned it, because the conditions happen to permit complexity, and you're here, conscious, aware, understanding that you're the universe experiencing itself. That's not defeat by vastness. That's triumph over limitation. In the war between mystery and understanding, understanding wins, slowly, incrementally, through patience. Ray Davis waiting 30 years. LIGO team building for 55 years. Andre Linde refining models for decades. Each contributed. Each advanced understanding one step. Each demonstrated that patience, rigor, and refusal to quit eventually produce truth. The cosmic horizon doesn't mark where reality ends. It marks where current observation ends. Technology improves. New instruments launch. What was unobservable becomes observable. Boundaries recede, not infinitely. Some limits are absolute. Quantum mechanics, cosmic expansion, mathematical incompleteness. But within those limits, progress continues. Questions get answered. New questions emerge. The cycle repeats, and you're part of it by existing, by being curious, by reading these words and thinking about cosmic horizons and bubble universes and holographic boundaries and self-referential observation loops. You're the universe knowing itself. Locally, briefly, magnificently. The observable universe, 93 billion light-years across. One bubble among possibly infinite bubbles. One holographic projection among endless projections. One temporary spike of order in an ocean of entropy, and you arrangement of atoms, pattern of information, brief computation and cosmic substrate you understand. Not completely. No one does. The deepest questions remain open. Dark energy unexplained. Inflation unproven. Multiverse unconfirmed. Holography conjectured. Simulation unfalsifiable. Wheeler's loop beautiful but speculative, but you understand the shape of it, the structure, the pattern. You understand that the universe is larger than you can see, older than intuition suggests, stranger than common sense permits. You understand that observation participates in reality, that consciousness isn't peripheral but fundamental, that you're not separate from the cosmos but integral to it. And that understanding that moment when the pieces click into place and you really see what you're inside of, that's not diminishment, that's elevation. That's the triumph of the human mind over cosmic mystery. That's patience rewarded, curiosity vindicated, generations of effort bearing fruit. Mystery remains, always will. The horizon recedes but never vanishes. But understanding grows, slowly, patiently, triumphantly. And in the cosmic war between the vastness that could crush meaning and the consciousness that creates it, consciousness wins. You are here. You understand. That's victory.